Enriched uranium is a type of uranium in which the percent composition of uranium-235 and uranium-234, 235U is the only nuclide existing in nature that is fissile with thermal neutrons. Enriched uranium is a critical component for both civil nuclear power generation and military nuclear weapons. The International Atomic Energy Agency attempts to monitor and control enriched uranium supplies and processes in its efforts to ensure nuclear power generation safety and curb nuclear weapons proliferation. There are about 2,000 tons of highly enriched uranium in the world, produced mostly for nuclear power, nuclear weapons, naval propulsion, and smaller quantities for research reactors. The 238U remaining after enrichment is known as depleted uranium and is considerably less radioactive than even natural uranium. Though still very dense and extremely hazardous in granulated form, such granules are a natural byproduct of the shearing action that makes it useful for armor-penetrating weapons and radiation shielding. Uranium as it is taken directly from the Earth is not suitable as fuel for most nuclear reactors and requires additional processes to make it usable. Uranium is mined either underground or in an open pit depending on the depth at which it is found. After the uranium ore is mined, it must go through a milling process to extract the uranium from the ore. This is accomplished by a combination of chemical processes with the end product being concentrated. Uranium oxide, which is known as yellow cake, contains roughly 60% uranium, whereas the ore typically contains less than 1% uranium and as little as 0.1% uranium. After the milling process is complete, the uranium must next undergo a process of conversion to either uranium dioxide, which can be used as the fuel for those types of reactors that do not require enriched uranium, or into uranium hexafluoride, which can be enriched to produce fuel for the majority of types of reactors. Naturally occurring uranium is made of a mixture of 235U and 238U. The 235U is fissile, meaning it is easily split with neutrons, while the remainder is 238U. But in nature, more than 99% of the extracted ore is 238U. Most nuclear reactors require enriched uranium, which is uranium with higher concentrations of 235U ranging between 3.5% and 4.5%. There are two commercial enrichment processes, gaseous diffusion and gas centrifugation. Both enrichment processes involve the use of uranium hexafluoride and produce enriched uranium oxide. Reprocessed uranium and creating neptunium-237, which would be one of the more mobile and troublesome radionuclides in deep geological repository. Disposal of nuclear waste. Low enriched uranium has a lower than 20% concentration of 235U. For instance, in commercial LWR, the most prevalent power reactors in the world, uranium is enriched to 3 to 5% 235U. High SALU is enriched from 5 to 20%. Fresh Lu used in research reactors is usually enriched 12 to 19.75% 235U. The latter concentration is used to replace HEU fuels when converting to Lu. Highly enriched uranium has a 20% or higher concentration of 235U. The fissile uranium in nuclear weapon primaries usually contains 85% or more of 235U, known as weapons grade, though theoretically for an implosion design, a minimum of 20% could be sufficient, although it would require hundreds of kilograms of material and would not be practical to design. Even lower enrichment is hypothetically possible, but as the enrichment percentage decreases, the critical mass for unmoderated fast neutrons rapidly increases, with, for example, an infinite mass of 5.4% 235U being required. For criticality experiments, enrichment of uranium to over 97% has been accomplished. The very first uranium bomb, Little Boy, dropped by the United States on Hiroshima in 1945, used 64 kilograms of 80% enriched uranium, wrapping the weapon's fissile core in a neutron reflector in diameter. Later US nuclear weapons usually use plutonium-239 in the primary stage. But the jacket or tamper secondary stage, which is compressed by the primary nuclear explosion, often uses HEU with enrichment between 40% and 80% along with the fusion fuel lithium deuteride. For the secondary of a large nuclear weapon, the higher critical mass of less enriched uranium can be an advantage as it allows the core at explosion time to contain a larger amount of fuel. The 238U is not said to be fissile but still is fissionable by fast neutrons such as the ones produced during DT fusion. HEU is also used in fast neutron reactors, whose cores require about 20% or more of fissile material, as well as in naval reactors, where it often contains at least 50% 235U, but typically does not exceed 90%. The Fermi 1 commercial fast reactor prototype used HEU with 26.5% 235U. Significant quantities of HEU are used in the production of medical isotopes. For example, molybdenum-99 for technetium-99 meters generators. Isotope separation is difficult because two isotopes of the same